Let's practice improving our understanding of prime numbers, composite numbers, and prime factorizations together. For each of these given practice problems, we're going to go ahead and write the prime factorization for each number, write the number of factors that each of these numbers has, and then write whether each number is either prime, composite, or neither. And just a reminder, the first few prime numbers are going to be 2, 3, 5, 7, 11, 13, 17, 19, and 23. While there's definitely more prime numbers after that, these are going to be the main ones that we're going to use in our prime factorizations. They're the most common. For number 1, we have the number 12. Let's go ahead and take this 12 and think of any two factors that multiply to get to 12 except for 1 times 12. I'm going to use 2 times 6 here, and then we're going to try to see if we have any prime numbers. So this 2 is definitely a prime number. It's the only even one. But the 6 here is not, right? It's not on the list of prime numbers. So we can go ahead and break this down further, and we can break it into 2 times 3. Now again, 2 is a prime number, so we're always going to circle it, and 3 is also a prime number. So at this point, we have all primes at the bottom, so we can go ahead and write our prime factorization as 12 is equal to 2 times 2 times 3. That's go ahead and using just all the factors written out. However, if we go ahead and see that we have 2 of these 2's, using exponents, we can write this as 2 to the second power times 3. So whether you write your prime factorization like this as a multiplication sentence all the way out, or you use exponents, either form of this is good for the prime factorization. Now, to determine the number of factors that 12 has, I recommend using the exponent form of the prime factorization, so this 2 to the second power times 3, because what you can do here is you can actually go ahead and take this prime factorization, it's 2 to the second power and 3 to the first power, right? There's 2 2's and 1 3, and if you go ahead and add 1 to each of these exponents and then multiply those sums together, you're actually going to get the total number of factors that the number has. So the 2 plus 1, that's going to equal 3, and then that 1 plus 1 is going to equal 2. So if we multiply 3 by 2, that's going to be 6. So we now know that 12 has a total of 6 factors. All right, so right there we have the total number of factors that 12 has. We're not listing them right now, but we're just going on saying that we know that 12 has 6 of these factors. Finally, in determining whether 12 is prime, composite, or neither, we just look at the number of factors. So we know it has 6. Because it has more than 2 factors, it's not prime, and because it doesn't have an infinite, then it's not neither. So 12 must be a composite number. There we go. For number 2, we have the number 15. So we're going to take this number 15 and think of any two factors. Now, if you know your divisibility rules, then hopefully we know that 3 times 5 equals 15. Now, it turns out that 3 is going to be a prime number, and 5 is also a prime number. So the prime factorization for 15 is quite short. It is just going to be 3 times 5. All right, and we actually can't even really write this using exponents. We could just write a 1 and a 1 for the exponents. I'm going to leave it like that just for now. If we're going to determine the number of factors, we can go ahead and write it like this 3 times 5, and then go ahead and write the 1 and the 1 in, right? Now, if we go ahead and add 1 to each of these exponents, we can add 1 and add 1. Then what we're going to get here is 1 plus 1 is 2, and then 1 plus 1 is 2, so 2 times 2 is going to equal 4. Which means that the number 15 is going to have exactly 4 factors. All right, so that's the number of factors that 15 has, this nice little shortcut that we can use using the prime factorizations and adding 1 to each of their exponents. Finally, if it has more than 2 factors, like this one does, and not an infinite number, then we know that 15 is going to be called a composite number. All right, so there we go. We answered all 3 parts, and we know a little bit more about the number 15. For number 3, we have the number 20. So what I'm going to do is start off with 2 factors. I know it's an even number, so I'm going to do 2 times 10. I know that 2 is prime, so I'm going to go ahead and circle it. And this 10 is composite. It's divisible by 2, so we can go ahead and put it 2 times 5. Now again, 2 is prime, and 5 is also prime. So for the prime factorization for 20 here, what I'm going to go ahead and do is move up just a little bit and write that 20 is equal to 2 multiplied by 2 multiplied by 5. So this is one way of writing the prime factorization. And if you want to go ahead and use exponents, which I'm going to do here as well, then we could say that this is 2 to the second power, because there's 2 2's multiplied together, and there's going to be 1 5. So this right here would be the exponent form for the prime factorization. Now, to figure out the total number of factors 20 has, let's go ahead and take the prime factorization using exponents and add 1 to each of their powers. So again, remember this 5 has a invisible 1 there. It lets us know they have 1 5. You're gonna add 1 to that. 2 plus 1 is gonna be 3, 1 plus 1 is going to be 2, so 3 times 2 is gonna be 6. So we know that the number 20 has exactly 6 factors. Okay, so let's go ahead and just say that we know the total number of factors that 20 has. Now it has more than 2 factors here, but not an infinite amount. So we know that 20 is defined as a composite number. All right, so there we go. We know a little bit more about the number 20 now. For number 4, we have the number 21. So let's think about factors of 21 or what it's divisible by. I know it's divisible by 3, so 3 times 7 is equal to 21. 3 is prime, so I'm going to circle it. 7 is also prime, so I'm going to circle that. So it looks like the prime factorization is very short. It's just going to be 3 times 7, okay? We're going to go ahead and leave it just like this. Now, if we want to go ahead and write the number of factors it has, let's go ahead and just take this 3 multiplied by 7. Keep in mind that this is really 3 to the first and 7 to the first. There's 1 of each of those. And we can go ahead and add 1 and add 1 to each of these powers. 1 plus 1 is 2, and 1 plus 1 is 2, so 2 times 2 is going to be 4. So the number 21 has exactly 4 factors. Okay? And if we know it has 4 factors, then that's definitely more than 2, and it's not an infinite amount of factors. So we know that 21 is a composite number. Go ahead and write composite number. Cool. So that's it for number 4. For number 5, we have the number 17, so let's go ahead and write 17 just like this. Now it turns out 17 is already a prime number. If you go through your divisibility rules, you actually can't think of anything, hopefully, that would go into it that is a whole number. So 17's prime factorization is actually just 17, okay? It's just like that. Now if you want to go ahead and write the number of factors it has, take the 17, which is 17 to the first power. If we go ahead and add 1 to its exponent, 1 plus 1 is going to be 2. So it's actually just going to be 2 factors, right? It doesn't have anything else that goes into it, so it's just 1 times 17, and that's it, okay? So we know 17 has 2 factors, and the definition of a prime number is it has exactly 2 factors. So number 17 we can define as a prime number, because it has exactly 2 factors. For number 6, we have the number 2. So let's go ahead and take this 2 and see if we can write a prime factorization. But remember, 2 is the only even prime number out there, so it's already prime. So the prime factorization for 2 is just 2. All right, that's it. If you want to know how many factors it has, this is just like number 5, where if we had the number 17. So if we take the number 2, which is 2 to the first power, and add 1 to it, then that would be 2. So that would be 2 factors, which hopefully makes sense because we've circled 2 a bunch of times in our prime factorizations. So we know 2 has 2 factors. It literally just has 1 times 2. And so 2 is what we would call a prime number. All right, on to number 7. For number 7, we have the number 27. So let's go ahead and take this 27. 2 plus 7 is 9, so we know this is divisible by 3 and 9. So actually 3 times 9 is 27, and 3 is a prime number, so we can go ahead and circle that. And 9 is still composite. 9 can divide by 3, so we can get 3 times 3 to equal 9 as well. So we have a bunch of these 3's. We have 3 of these 3, so the prime factorization for 27 we can write as 3 multiplied by 3 multiplied by 3. That's one way of writing the prime factorization for 27. But using exponents, we could also use shorthand and write this as 3 to the third power, and this would also be the prime factorization just using exponents instead. Now to determine the number of factors, let's go ahead and take this prime factorization using exponents as 3 to the third power. Let's go ahead and add 1 to the exponent, so 3 plus 1 is 4. So the number 27 is going to have exactly 4 factors. All right, so let's go ahead and box that because that's how many factors 27 has. And because it has more than 2 factors, but not an infinite number of factors, then 27 is called a composite number. Composite number. Alrighty, so now we know a little bit more about the number 27. All right, for number 8, we have the number 48. So let's go ahead and write this 48 and think of 2 factors that multiply. Think of our multiplication facts. Maybe we can come up with 6 times 8, that does equal 48. Neither of these numbers are prime, so they can still be broken down. So maybe for 6, we'll do a 2 and a 3, and those are both prime numbers. So let's go ahead and circle those. 2 is prime, 3 is prime, and this 8 here is definitely still composite. So let's go ahead and break 8 into maybe 2 times 4. Now 2 again is prime, but this 4 is composite. So let's break this 4 down into 2 times 2. All right, so at this point we have all of the prime factors that multiply to get to 48. So we can write the prime factorization for 48 is going to be, looks like we have 1, 2, 3, 4 2s. So 1, 2, 3, and 4. So it's 4 2s multiplied by a 3. Okay, so 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 3 is 48. So this is a longer prime factorization, but it appears to be correct. All right. Now, if you want to use exponents for this, we can go ahead and say that we have 2 to the 4th power multiplied by 3, right? So it's a little shorter, but this is it using exponents. All right, next we're going to go ahead and figure out how many factors it has. So let's take this prime factorization using exponents of 2 to the 4th power multiplied by 3 to the 1st power. Let's go ahead and add 1 to each of these exponents, so 4 plus 1 and 1 plus 1. 4 plus 1 is going to be 5, and 1 plus 1 is going to be 2, so 5 times 2 is 10. So since 5 times 2 is equal to 10, we know that the number 48 has exactly 10 factors, so a lot more than all the previous ones we've looked at, but 48 has quite a bit of factors here. All right, because it has more than 2 factors but not an infinite amount, we know that this is a composite number. All right, so that's it for number 8. For number 9, we have the number 56. Let's go ahead and write 56. Now, what does 56 break into? Well, I'm thinking maybe 7 times 8 equals 56. 7 is a prime number, so I'm going to go ahead and circle it. Now, 8 can break into 2 times 4. 2 is going to be a prime number, so let's go ahead and circle it. And then 4 breaks into 2 times 2. So at this point, we have all of our prime factors that multiply to get to 56, okay? So if we're going to go ahead and write this out, we can write this as 2 times 2 times 2 times 7. That would equal 56. Again, those 3 2's together make 8, so 8 times 7 is 56. And using exponents here, we can say this is 2 to the 3rd power multiplied by 7. So that's our exponent form for our prime factorization. Now for the number of factors, let's go ahead and write this is 2 to the 3rd power multiplied by 7 to the 1st power. If we add 1 to this 3 and add 1 to this 1, 3 plus 1 is going to be 4, and 1 plus 1 is going to be 2. So 4 times 2 is 8. So we know the number 56 has 8 factors. Alrighty, now if we're going to go ahead and see if it's prime or composite, well, it has more than 2 factors but not an infinite number, so we can say it is composite. Here's number 10. For number 10, we have the number 72, so let's take this 72, let's break it down. I'm thinking maybe we can start with 9 times 8, so I'm going to put 9 multiplied by 8. I don't think either of these are prime, so we can keep on going here. So 9 we can maybe break into 3 times 3, and 3's are definitely prime. We've seen those a lot in this practice set. And so we have 3 times 3, and then it's 8. Let's break this into maybe 2 times 4. I'm going to put the prime number on the inside so we have more space. And 4 is composite, so we can break that into 2 times 2. And it looks like we now are done with our tree. So for 72, the prime factorization looks like we have 3 2s, so 2 times 2 times 2, and then 2 3s. All right, so there's our prime factorization. If you want to use exponents here, we can go ahead and say that this is going to be 2 to the 3rd power multiplied by 3 to the 2nd power, and this would be okay as well. Okay. Now to figure out how many factors that 72 has, let's go ahead and use the exponent form. So 2 to the 3rd power multiplied by 3 to the 2nd power. We can go ahead and add 1 to each of these powers. 3 plus 1 is 4, 2 plus 1 equals 3, so 4 times 3 is going to equal 12. So 72 is going to have 12 factors. Okay, so now we know how many factors 72 has, which is quite a bit, 12 factors here. And because it has more than 2 but not an infinite number of factors, then it is definitely a composite number. For number 11, we have the number 81 here. So for 81, let's go ahead and break this down. I think maybe the most common thing you might think of is going to be 9 times 9 for 81. Now again, 9 is composite. It's going to break into 3 times 3. These are prime numbers, so I'm going to circle the 3's. It looks like this 9 over here is also going to break into 3 times 3. They're going to be the same. And so we can go ahead and circle all of these. So turns out 81 just breaks into the product of 3 times 3 times 3 times 3. That's going to be it just written out as one long sentence. And then using exponents, we can say this is going to be 3 to the 4th power. All right, cool. Now if we're going to go ahead and find the number of factors, let's take this 3 to the 4th power, the exponent form, and just add 1. So 4 plus 1 is going to be 5. Turns out 81 is going to be having 5 factors. And it turns out that all numbers will have an odd number of factors if it's a perfect square. So 81 is a perfect square, so we should have an odd number of factors, just because 9 times 9 is 81, so you don't repeat that 9, okay? And once again, since it has more than 2 factors but not an infinite number of factors, then 81 is composite. For number 12, we have the number 0. Now keep in mind that 0 is neither prime nor composite, so it does not have a prime factorization, so I'm just going to write NA for not applicable, or none. You could write as well. If you want to know how many factors it is, you can't really write a prime factorization, so what you can write is that it has infinite factors, so infinite factors. And that hopefully makes sense because anything times 0 is still going to be 0, right? So you could say like 0 times 1, 0 times 2, 0 times 3, 0 times 4. So because it has infinite factors here, it's going to be neither prime nor composite. All right, so I'm just going to say neither and nor. All right, just so we're clear that 0 is not a prime number and it's not a composite number. It fits in this strange little category where you actually have an infinite number of factors, so not prime, not composite. For 13, we have the number 144, so this is a pretty big number here. So let's go ahead and see if we can break this down now. 144, I think maybe the most common fact that we're going to use is maybe 12 times 12, that's 144. And again, feel free to use divisibility rules. If you wanted to add 1 plus 4 to get 9, you could divide it by 9 or 3. You could also divide it by 2 in the beginning if you'd like to. So many things we could do here. 12 is still composite. I'm going to break this into a 2 and a 6. I'm going to put my 2 on the inside so it branches out a little bit further so I don't run out of space. And then for the 6, I'm going to break this into 2 and 3. So 3 is a prime number and 2 is a prime number. Now this 12 over here is just going to be duplicates. So I'm going to put a 2 and a 6. And again, I'm going to put my prime number on the inside so that I have more space and the 6 can keep branching out side here. And then 6 breaks into 2 and 3. So both sides of the tree should be pretty identical here. And it's because 144 is a perfect square. So 144, how many 2's do we have? Looks like we have 4 2's. So 1, 2, 2 2's, 3 2's, 4 2's, and then 2 3's. So 2 of these 3's here. So this would be one version of the prime factorization. And if you want to use exponents, we can say this is 2 to the 4th power multiplied by 3 to the 2nd power. Alrighty, cool. So just like that, we have our prime factorizations. And using the one with exponents, this 2 to the 4th power times 3 to the 2nd power, let's go ahead and add 1 to each of their exponents. So 4 plus 1 is going to be 5. 2 plus 1 is going to be 3. So 5 times 3 is going to be 15. So the number 144 has 15 factors. So that's a lot of factors for one number. Because it has more than 2 factors, but not an infinite number of factors like 0, then we know that this is a composite number. Alrighty, so go ahead and put a box around that and we're done with number 13. For number 14, we have the number 57, so let's take this 57 and break it down. Now if you're wondering if you can break it down by anything, go through your divisibility rules. Can't divide by 2, but it can divide by 3 just because 5 plus 7 is 12, and 12 is a multiple of 3. So it turns out that 3 times 19 is 57. 3 is a prime number and 19 is also a prime number. So the prime factorization for 57 is going to be 3 times 19. And since there's only one of each of these, we can't write using exponents really. I mean, I'll go ahead and do so and put these little ones in. So 3 to the 1st power multiplied by 19 to the 1st power. Technically that's using exponents, right? We add 1 to both of these exponents, we get 2 and then times 2. So that's going to be 4. So 57 has 4 factors. It's going to be 1 in 57, and it's also going to be 3 times 19. So those are the 4 factors. And because it has more than 2 factors, but not an infinite amount of factors, it is composite. All right, cool. So there is number 14. And if you thought 57 was prime, just try to use your divisibility rules to check that, okay? For number 15, we have the number 1. So for 1, this is, again, neither prime nor composite. It's kind of like number 12, where we had the number 0. So 1 has only one factor. So it only has one factor. I'm going to go ahead and write that. And that's because 1 times 1 is 1. It's a perfect square, right? So because 1 only has one factor, then we can't say it is prime. Prime numbers have 2 factors. And it can't say it's composite because composite numbers have more than 2 factors, but not infinite. So because the number 1 only has one factor, and it's not prime because prime has 2 factors and composite numbers have more than 2 factors, then we can say that the number 1 is also in this neither nor category. So just try to remember that 0 and 1 are very special. They're kind of strange numbers where they are neither prime nor composite because of having only one factor or infinite factors. Finally, for number 16, we have this number 91, and try to see our divisibility rules. Now, I don't think it's divisible by 2 or 3 or 4 or 5 or 6. We're kind of running out in some numbers, so if we go ahead and take this 1 and double it, that's 2. 9 minus 2 is 7, which is a multiple of 7, so we know that we can divide this by 7. Okay, so I know 7 times 10 is 70, which gives us 21 away from 91. So I'm going to go with 13 here. So 7 times 13 is going to be 91. So our divisibility rules can help us out a little bit. And so 91's prime factorization is just 7 times 13, and we can stop right there. Now, to figure out how many factors 91 has, we have the 7 to the first power multiplied by 13 to the first power. If we go ahead and add 1 to each of these exponents, 1 plus 1 is 2, 1 plus 1 is 2, so 2 times 2 is equal to 4. So the number 91 has 4 factors. So you can think of them as 1 times 91 is 2 of the factors, and then 7 times 13 as the other 2 factors. Okay? And because it has 4 factors, which is more than 2 factors, then we know that this is a composite number. All right, so there you have 16 different practice problems on deciding whether numbers were prime or composite, also how many factors they have, and also writing their prime factorizations using a multiplication sentence and exponents as a shortcut. If you found this video helpful, please consider giving it a thumbs up, and as always, keep up the great work, and I'll see you in the next one.